So what I'm going to do today now, I'm going to explain once more how to find coordinates in orthogonal versus orthonormal basis. Okay, so I think there was some confusion about that, and I just want to make it right. Okay, so first we start with a vector. Say we have a vector x, okay, which has a representation of this form, CIVI. You can think about the simplest example. Say you have a vector in a two-dimensional space. Say you have a vector 1, 2, right? And you can present it as 1 times 1, 0 plus 2 times 0, 1. Okay? So in this case, 1 is going to be C1, 2 is going to be C2. So V1 in this case will be 1, 0. V2 will be 0, 1. C1 will be 1. And C2 will be 2. Okay? So that's our setup. We want to find now in each system right now, if we have a rotation, let's say we have this is our usual coordinate system, but we can rotate it like this. It will still have 90 degrees, and every vector, right, will have a presentation of those two vectors in a new coordinate system. And what our goal is, right, is to find this formula for these guys. Okay? So we are going to distinguish two cases. The first case is when VI are orthonormal. That's the simpler case. So if VI are orthonormal, it means that VI, Vj, the scalar product, this equals to 0, okay? And that Vi, scalar product with Vi itself, equals to 1, okay? So that's what we call an orthonormal basis. So for example, 1, 0 and 0, 1 will be an orthonormal basis. Why? Because V1, right, is going to be 1 times 1 plus 0 times 0, so it's 1, right? And 0, 1 will be 0 times 0 plus 1 times 1, which is going to be 1. But and V1 scalar product with V2 is actually going to be 1, right? So V1 dot V2, or, so it's 1 times 0 plus 0 times 1 is equal to 0. So that's an example of an orthonormal basis. It's the simplest orthonormal basis possible, okay? Another example of an orthonormal basis is something of this form. 1 over square root of 2 minus 1 over square root of 2, and 1 over square root of 2 and 1 over square root of 2. This is like my favorite one, okay? Now, if you look at the norm of this guy, right, it's going to be half plus half equals 1. Okay, and these guys, well, and they're actually orthogonal because if you multiply and sum, right, you will get 0. Now, if you have an orthonormal basis, okay, the formula to find those coordinates is actually very simple, very, very simple. All you need to do, okay, is to take x and make a scalar product with Vi. This is going to be your Ci. If this is an orthonormal basis, we will talk in a minute what happens if it's not an orthonormal basis. But if it's an orthonormal basis, it's actually very simple. So for example, okay, if you have a vector of the form 1, 0, to find its coordinates in this basis, all you need to do, right, is to actually make a scalar product of 1, 0 with these guys. So if you take 1, 0 with 1 over square root of 2, right, you're going to get 1 over square root of 2. Okay? If you now get 1, 0 with the next one, with this basis, you will also get 1 over square root of 2. And indeed, if you just look at that, you are going to get that 1 over square root of 2 times 1 over square root of 2 square 1 square root of 2 plus 1 over square root of 2 times 1 over square root of 2 minus 1 over square root of 2, right, equals to actually here, right, you will get half plus half in the first coordinate in the second coordinate, you will get 0, so you will actually get 1, 0. And you're done, you see? You see how simple it is? It's really, really, really simple. Okay? There is nothing to panic about. All you need to remember, right, is how to do scalar products. That's all. And scalar product is actually very simple. You have two n tuples. If you have alpha 1, yada, 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 alpha n, and beta 1, yada, 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 until beta n, all you do, right, is just alpha I, beta I. That's it. That's all there is to it. Okay? It's really nothing. I mean, it's really nothing. All you need to do is just to concentrate on the formulas and you'll be fine. Okay? Now, what happens when you have orthogonal? What does it mean to be orthogonal? Okay? Orthogonal means that you are actually almost orthonormal but without this condition. So all you have is that Vi, Vj, okay, scalar product equals 0, or Vi dot Vj equals 0, or Vi Vj equals 0. So any of those three terms, right, they denote the scalar product. And people are actually interchangeably use those things one with another. So if you see some book which uses this, or you see some books that uses this, or you see some books that uses this, you should never panic, right? Because they all refer to this simple thing. Okay? Now, all you do, so if you have x, and now Vi is your orthogonal basis. Okay? All you need to do in order to find your coordinate, Ci, is going to be x, okay, scalar product with Vi, divided by the scalar product of Vi with itself. That's all. That's it. Okay? So it's the same as here, but you just divide by the scalar product of the element basis itself. So for example, okay, if instead of 1, 0, okay, you would get not 1, 0, but and 0, 1, but maybe 1, 2, 0, and 0, 1, right? So this is an orthogonal basis. Now, in order for you to normalize, all you need to do here is to divide by 2. You know, you have the scalar product, and here you have the first, so the second one will not change. The first one, right, all you need to do is just to divide this guy by 4, right? Because the norm of 2, 2, 2, 0, 2, 0, 2, 0, when you multiply it, you'll get 4. Okay? So that's it. I mean, it's really, 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 really easy if you organize it in your head, right? And you just say, okay, I have two cases, one orthogonal, another orthonormal, and the orthogonal is a little bit more difficult. Now, pay attention that if Vi is orthonormal, right, Vi is 1, so this is actually goes back to the previous formula. All right? So that's all I wanted to say today, and I just hope that you'll have a nice day. Thank you very much.